Hi, my name is Andrew McLaren. Today we're going to go over acids and bases and how they appear on the AP exam. This is going to be for the year 2024. I did a video in 2023 about this, and my prediction's very close to being right. So there's a focus on this exam that I think a lot of teachers go a little bit beyond. So we want to get the big picture. And the big picture is right here. There's 2 points that you really need to know. You need to know how to recognize the equivalence and the half equivalence point, and you need to know the significance of the x and the y axes when you're at those points. So you really need to be able to solve, especially with the half equivalence point, know what this is, as well as know what these volumes mean in the problems. So I'll clarify that in a little drawing and some notes. Then we'll actually do some example problems. And you can skip the notes if you'd like. And if you get confused, you could go back and watch that part. So if you've really got a good understanding of this titration curve, you're going to be fine on the AP exam. Now you need to understand the half equivalence point is when 50% of the acid, maybe represented by HA, has been pulled forward into A minus. So those are the conjugates, like HA and A minus are conjugates. So the half equivalence point, you've got equal amounts of HA and A minus because half of HA has been pulled forward. In other words, the pKa is equal to the pH, because if you think about our Henderson-Hassel Bach equation right here, if A minus and HA, if that ratio is just 1 to 1, then the logarithm of 1 is 0, and so that kind of simplifies the Henderson-Hassel Bach equation to the pH is equal to the pKa. Now, most of the students that I know that I've worked with kind of know this one, but then they get kind of confused about the equivalence point and the moles and like what is equal and where. And so it's really important to clarify conjugates versus the acid and bases that are being titrated against each other. So usually there's, in this case, we have an acid where half it's been pulled forward at the half equivalence point by some strong base. So maybe there's some volume of NaOH added. That could be what we're talking about on this axis here, on our x-axis, and then you've got your pH on the y. So there's a formula that you'll probably have seen with like CaVa is equal to CbVb. That's only true for the equivalence point because the acid that you've titrated with the base that you've titrated, those amounts are equal now. So now all of HA has been turned into its conjugate by this strong base. So the moles of HA are equal to the moles of NaOH. In other words, these things are equal to each other. And if we're going with this stuff being gray, then I suppose that we could make this NaOH the gray thing to show that that is the titrated base, which is very different than the conjugate base for the acid that we're talking about. And there's a couple different ways that you can make these things, but you want to think about the titration curve here because it's a nice way of thinking about the whole thing as a system. So if we are talking about an ideal buffer, you also need to be able to recognize what an ideal buffer is. And that's when there's very little changes in pH when you're either adding an acid or a base. AKA, this is where the line is flat because, slope is change in its pH over change in volume. So this is the smallest change in pH for a change in volume right here when it's flat. So the ideal buffer is at the half equivalence point. So you need to be able to recognize if they're describing a buffer that you're at that half equivalence point, because that's going to help you figure out how many amounts of things you need or what strategy you're going to do. One other thing to just keep in mind is that if you're at the half equivalence point, the volume of base is half of that of the volume of the at the equivalence point. So you'll have this VB here for the equivalence point, and then what I've got in red right here, that's your VB right there. So this is just a volume that you might need to be able to solve for based off of them have moles present of the acid and knowing the concentration of the base, and you solve for that volume of the base. In other words, you're probably going to know this, and that, so you can solve for that most of the time. And if you can do that at the equivalence point, you should be able to kind of figure out backwards how much volume you would have at the half equivalence point, because it would be half that volume to give you half that many moles. So that's the main big picture on all this. To make a buffer, a lot of times you gotta have this strong acid with a weak base, but this is pulling that forward. So this strong acid is pulling the strong base. So or the weak base, and so you've got this weak base with its conjugate present. Or you might have like a weak acid with a strong base, and so that is pulling the weak acid to making some of its conjugate base. Or maybe you just have a good amount of conjugates. So you might do that if you have some HA and A minus put into solution. And that's usually with some sort of salt or something. So one of these will be like the acid and one will be the base, and you're just like, I'm putting in equal moles of these two things present. So that's very different. So to make a buffer, you're either using an acid with a different base that's titrated to make the conjugate, or vice versa, or you actually just have the conjugates and you're just like, okay, let's put those in solution and put them in roughly equal amounts of those two conjugates. But if you were to put an equal amount of this weak acid and strong base, you're not at the half equivalence point. Now you're at the equivalence point. So you've gone too far for a buffer solution. So while this question appears a bit different than other ones that we've talked about in the past, this is very important to recognize that they're talking about making a good buffer. So this is the ideal buffer solution. So we're at like a half equivalence point. In other words, the amount of HA is equal to A minus. So knowing that information, or like the pH is equal to the pKa, that might be relevant here. So I know where I am in terms of like a titration curve, though this doesn't sound like it is like a titration. It sounds to me like you're like, I'm having some amount of the HA and some amount of the A minus, because they're giving you the two conjugates. We're trying to get there to be about equal moles of these two things. It's a half equivalence point, but that's the half with like the strong base or whatever that you usually use to transform this acid into its conjugate base. So part A is pretty straightforward. That's just a molar mass calculation right there. So you've just got the moles. I'm going to skip that just to focus on the acid base component here. So that right there is going to tell you the amount of grams of the stuff that that you have present of this CH3 and H3Cl. So there's that amount of grams. And they've basically, what they've given us here is they've already taken like this, the Ca and Va, and they've multiplied those two together, and they've given us the moles of A, of the acid. So that is this thing right here. So we have the moles of HA. Now we're saying like, okay, let's say that you want to have the same amount of moles of the base. So they're making it so we have the same amount of moles of that base present if we have that many grams of base. So this is some grams of the base that we're going to be having put in this solution. So to do that, you basically need to weigh out, they've got some procedure stuff here. So you're going to need to weigh grams from part A. And they've given you a couple things here. You're probably going to need to use the weighing paper, because you're putting some solid on a scale. You're probably going to like use a little scapula to get some of the solid on the weighing paper while it's on that balance. So there's definitely all of that going on here. And I can see like, okay, so we've got that solid, and now we're going to end up mixing that with the amount of acid that we already had present, and that would make an ideal buffer solution. There is this part 4 right here, there you want to rinse the burette with the thing that you're going to end up putting in this CH3NH2 solution, or the 0.1 molar of that, because if you don't, it's going to lead to dilution. And that's just kind of an experimental thing. If you think about it, if you've even got a little bit of water in that, when you add in the acid, you've kind of diluted it, so you've kind of thrown off the concentration. So you got to be careful there. But if we do those two things, then the pH should be close to our pKa value for this acid. And it should buffer nicely around that. So if you're thinking about this like titration curve, we're around here if we've got the two things equal to each other. And it sounds like we've got equal moles of HA and A minus present in this situation. So you can see that this is very closely related to what I was talking about here, where you need to recognize what's going on with conjugates versus titrated acids and bases. Really need to clarify the difference between those two. So they actually give us the pKb for this chemical and relate that to the pH. And then they've described for us, like, okay, you've got now half the concentration. So we've got half the concentration of one of these things. And we've got half the mass of the other. So you've cut both these numbers in half. So if you think about your Henderson-Hasselbalch equation, the pH is equal to the pKa plus the log of these two things, the A minus over the HA. Because you have cut both of these numbers in half, it's kind of like having a 1/2 and over a 1/2. So the ratio, this still cancels out, and you still have the pKa equal to the pH. So these should be equal. So the ratio between these two things is still equal. So you can see that this is not that hard of a calculation. It has a pretty complicated equation in there, but it should be coming out to the same. You can think about them competing for space, similar amounts. And then we have this guy here, which is interesting. So they've got a particle representation here, a particulate diagram. So they're showing some acid. And this is going over the definition of a strong acid versus a weak acid. So with a strong acid, it is going to go 100% forward. With a weak acid, you're going to need to use some sort of Ka to figure out how far forward it has gone normally. But then you can see that these Ka values, those are huge, which is kind of weird. These two things are what we would call strong acids. So normally you don't even give a Ka value for that because that's really, really big. Like this nitric acid is a weak acid, but it is a weak acid where like it's pretty decent. It's a stronger acid than its conjugate base is a base. So it's a pretty good acid here. Most things when you're working with Ka values are gonna be things like this. Like I don't even see college students even using these. So I'm a little bit irritated that the College Board would throw out Ka values that big. And it should just be saying that these are strong. So it's just 100% forward. And if you think about it, if you've got 1 mole, if you've got that big of a Ka, the whole mole's going forward. You've got like 0.0000001 left still as the conjugate. So these two things right here, they should be showing like almost all A minus. Like you might show like 1 HA still left, but it's going to be pretty much all A minus for those. Whereas if you're talking about a weak acid here, it's going to be almost all the this HA. So it's going to dissociate a bit. It's going to give off some acid, but not very much. So because we see that there's only one of these, and there's 1, 2, 3, 4, 5, 6, 7 of these, and there's one of these, it looks to me like there's been an acid that's dissociated like once. So you had like this HA break down once into the H3O plus and the A minus. So we also have the water here when we're actually thinking about H3O plus. So it looks like it went forward once over the 10. So it's not a perfect ratio with what this Ka value is, but it's kind of an okay representation. So only small amount dissociated. Must be weak. That's the main idea on this type of problem. And that's it. That's all I have from the 2024 kind of prep reviewing the stuff that you saw in the 2023 exam. I am going to show you 2 problems briefly, just so you get some context. But if you want to learn more, I have a couple different videos on acids bases, specifically for the AP chemistry exam, as well as more broadly, so you can understand this relationship between strong acid, weak base, and their conjugates. That's a really important thing to clarify, but you probably don't need to go much deeper than what we did in this video. So we have an example problem from 2019 here where we're seeing a titration. And so if we're thinking about this as a titration, it's kind of important to consider where we are on the titration curve. So if we think about this, there was some sort of reaction. They are talking about finishing this titration. So usually this is going to be a pH that's about 7. It's not going to be perfect depending on the strength of acid and base that you're working on, but it's about 7. And so there's this color change that's happening right here. So if we think about this, there's this lavender color that's being observed. And that's the end point of titration right here. So it's really important to recognize that we're talking about this end point, which is when we have the moles of the acid that are being titrated are equal to the moles of the base that are being titrated at the equivalence point. These are not the conjugates, so there is like this looks like there's some conjugate acid base kind of stuff going on. It's kind of complicated because this is being broken down right here with the carbon dioxide in the water, but you can think about it as there's like an equal amount of moles of these two things canceling out. And so the important thing that I want to highlight here is that they're asking you to do like something that looks like a CAVA is equal to moles of A. So they've given you the concentration here, and you get the volume from this diagram because there's going to be a change between these two. So this is a change in volume in the burette, which is going to be equal to the volume of the base added. I believe it's the base. It could be the acid that's added here. In any case, there's some sort of concentration and volume to moles relationship here. And what's important to note here is that they're talking about, okay, well, what if I've changed this concentration here? So we're using the same amount of stuff. So this is the same, and this right here is a lot more dilute. And it looks like it is like 10 times or maybe 20 times more dilute. So you're going to need to use 20 times more volume here, which is not going to be practical to do. So you can see if this concentration has gone down, then the volume has to go up to give the same amount of moles. So that's the main idea here. And you can see how this one formula and the idea of a titration curve come into play, though you don't have to do much of a complicated calculation with the ice charts or whatnot. The only problem that I've seen where you really have to do an ice chart on the FRQs, these free response questions, in like the last 4 or 5 years, the only one where you do an ice chart is this part right here. So if you're thinking about your titration curve, this is basically right at the beginning, what we're talking about right here for part B. So yes, you do have to do an ice chart, but it's very similar to your normal K equilibrium stuff that you did from the previous unit, so that should be manageable. Most acid-base problems that you're going to see on the exam are not going to be relating actual calculations along any points besides the equivalence and the half equivalence point. Like these, you don't really do calculations, but you may need to talk about like the relative amounts of HA and A minus at those different points. So I talked about this a bit in my previous video, but if you're down here versus up here, it's like too acidic, so it's mostly the HA, and then here it's a little bit too basic, so this is mostly A minus. Up above and below these, it's half equivalence point. So if they're equal to each other at that half equivalence point, if you're too far one way or the other, one is going to be more present. So you might have to say which one is more present, which in this case it should be mostly HA, because it's just dissociating a bit and there isn't any base that's been added to pull it forward. It's just got a bit of its conjugate being pulled forward naturally by its Ka. But yeah, that should be it. Thank you for McLearning with me. Before you go, please check out the following services that I offer with my business. So if you click the link in my videos, this goes to my website. I might be changing it from Podia because I'm no longer doing the interactive videos for sale. I might put those up for free. But most of my other services are linked here. So you can see that I've got like a Teachers Pay Teachers and a Wyzant. The Teachers Pay Teachers has a lot of my assessments that I have for like the NGSS, as well as lessons that I made when I was actually a teacher in the classroom. So I've got quite a few things like CERs and other things on there. If you want to get one-on-one live support from me, either like with science or like working on like teaching support lessons and that kind of stuff, you can sign up through Wyzant. I have a link to there where you can contact me there. And we can schedule hourly appointments. And I've got a few other things on here like a Facebook page and other social media. And if you're interested in getting professional development with me for like a team of teachers, a whole page with information on that. So yeah, feel free to check that out. Thank you.